I know I said I'd start this review at 5:07. Um, we, we, we might get started like a little bit early. I'll start with like a spiritual thought for you guys, and then 5:07 we'll start like the actual material. Um, because like when are you gonna have another TA give you a spiritual thought before you review? In my opinion, like that's never gonna happen. Like let's be honest. And pizza, like especially both, like the chances of that are very low. I'm just saying. So, um, so today pizza is not very like Last Supper-y. I don't think that's what they had. Uh, but they didn't have lamb as an option at Domino's, and I don't think you guys would like me if I did put lamb on the pizza. So we just didn't go for that. But today, if you didn't know, like Thursday was the day they had the Last Supper. They have like a Holy Week study plan and Gospel Library and everything. Super cool. And I was reading that this morning, um, and like the Last Supper is where Jesus taught a lot of like um, really like some of the most popular scriptures we have about love. And he one of those scriptures being, greater love hath no man than this, that a man laid down his life for his friends. And I thought it was super cool because the way that the Gospel Library like commented on this. I mean, I know it's not Gospel Library, the app, commenting. It's somebody that wrote it. But I mean, anyway, whoever it was, they said no one would blame him if he were thinking only of his own pain this night, but instead he used his last hours to gather, teach, prepare, and comfort those he loved. And I was thinking like maybe that hits a little bit different the week of finals, right? Because like I mean, if college like in general is a time where it's understandable to like focus on ourselves, then like certainly finals week is like, you know, especially a time where it's like super understandable to focus on ourselves, and kind of like close out to everything else. But just in this time of the Savior's life, like he was 100% focused on other people, and I just thought that was so powerful. Like combined with that teaching that he has, that greater love hath no man than this, that a man laid down his life for his friends, and Jesus laid down his entire life for me and for you, and that um, is like such a good lesson for college, just like in general. Like my first semester coming to BYU, I like I was doing homework all day, and I would do it like I would go into the library. You know those little booths that they have like on the side of the library, like on the second floor or the third floor or whatever. I would go into one of those booths, and I would just be doing like basically Math 290. Like that's the hardest class like I've ever taken to this day, and I was just like cramming Math 290 like all day. And so, like I did that for a few weeks, and then I was like, I can't like do this anymore. I need to live like differently. And so I decided to like change what I was doing. I decided to step back. I decided to intentionally be in places where I would get more social interaction. Um, and I mean, it made me happier. And honestly, I think it like improved my health and made my grades better uh, just by doing that. And like on my mission, I decided like before I came home from my mission, I decided that I would never like compromise the time I spent with God every day. Like I wouldn't let anything take priority over that. But since coming to BYU, I've really learned to also like next to my priority of spending time with God, like prioritize my relationships with other people. Um, and then like academics and everything else like falls in after that. And getting good grades is like, great. And, it's great to be in a school that's really academic, and it's great to push ourselves. Um, but I just think, being at BYU, like it's a temptation to just like fall into this way of prioritizing things where school comes before like everything else. And when your schedule gets busy, it's just like school, and then like you kill everything that's not school. And um, and I think that like as I've gone throughout school, and I feel like as most of us go throughout school, we'll feel like everyone around us is doing that. And I just found like I need to be the decision maker to be like, no, I'm gonna choose to not lose focus on what's most important. And honestly, what's most important is my relationship with God and my relationship with other people. I found that the more that I can give of my life, the more I give up of my life, the happier that I am. So I would encourage you guys, as you go throughout your BYU experience, to make that same decision, because it will make you a lot happier. So one of the reasons I'm a TA is because I can't help but think of like all the people that have spent their time and energy on me, and I just want to pay some of that forward. You know, I can't pay all of it forward. I can never do anything close to that, but I try to do like a fraction of what other people have done for me. So that is stuff. That is, I don't know what else to say about that. That's the gospel truth right there. But now we're going to talk about statistics. And we're going to talk about some really good statistics. I'm going to break this down like you've never seen it before. We're going to do A. Well, I mean, I'm going to cover the material for the class. I'm going to cover like all the material you guys should know and need to know. And then at the end, we can go over exam A and over questions. So that's what we're going to do. Okay, bringing this up. I was in 388 mode over here. Okay, so I was recently invited to this faraway land on the coast that's known for killer red sharks, and it's also got some great surfing. So the thing is that like even though these sharks are like super deadly, people surf anyway, and so there's a lot of shark attacks. And some people think there's this really popular ice cream brand over there called Vanilla Ice Incorporated. And basically people think that the more vanilla ice cream you consume, the more likely you are to get attacked by sharks. So knowing me to be an expert economist, they invited me over there to study this. So I conducted a survey, all right? It was a very simple 2-question survey. I asked people, number one, and this was like, you know, all different times, right? So it wasn't all at the same time. You know, I let it run for a couple years, different people every time. And I asked, how much ice cream did you consume in the last month? And did you or did you not get attacked by a shark? All right, pretty simple survey. And I got some results from that. What was that? Well, that's your opinion. Shoot. I did not even think about that one. Well, okay, we're done with that. Okay. So there is some distribution of these numbers. Okay, so we'll go with ice cream consumption. We'll go with we'll go with SH will mean you got attacked by a shark. 0 if you didn't get attacked by a shark. 1 if you got attacked by a shark. Ice cream consumption is in ounces. So both of these have true distributions. Okay, I took a survey, but like I'm never going to get everyone, but there is a true distribution of everyone, right? And there's some gospel truth around here of ice cream consumption. I don't know what it looks like. Maybe there's some amount of people that consume no ice cream, and then they, you know, it peaks out at some level and maybe it goes down like that. It seems reasonable for true value, and it has some true population mean called mu. All right, and it has some true variance. I'll call that variance sigma squared. Okay, this is what I can never know. Right, mu and sigma, if you didn't notice, are Greek letters, and just like the real Greeks, we will never know them. We will never come into contact with them. So I'm just gonna write like a little column here. So there are unknowables. These are Greek letters, like mu, and like sigma squared. Okay. mean, and variance, okay? And I'm going to call those thetas, right? These are unknowable things. And I'll call theta hats estimators that we can have for those things. So, for example, my estimator for my survey had an estimator called X bar, which is just the sample average, right? I had a sample average of 5 ounces of ice cream consumed, right? So X bar is my estimator of mu. All right. I also got a sample variance. Okay, I'll call that S squared. My sample variance happened to be 9, or in other words, the standard deviation of the sample was 3. But backing up here, put S squared up here. But backing up, like, the thing is that whereas my variable X has a distribution, a true distribution, my estimators also have true distributions. So like X bar has its own distribution, okay? So that estimator X bar is going to be, by the law of large numbers, we know that X bar is centered around what? Mu, okay? And by the central limit theorem, we actually also know something about the distribution of X bar. What's the distribution look like? It is normal, okay? And now for both of those things, those I can be more confident those hold true the closer my sample size is to infinity. So the larger sample size I have, the more confident I am that this distribution is centered around mu and that is normally distributed, okay? So those are my X bars, right? And so I got one X bar. This X bar comes from somewhere in this distribution, but I don't know where. It's more likely it comes from somewhere in the middle, but maybe I got unlucky. Maybe it came from like the edge, okay? So that's what happened, right? So I have my distribution of X bars, and you know that has its own, well, this would be, I could call this mu of X bar, but it's the same of mu of X, so I'll just leave it like that. But it does have its own unknowable variance, sigma squared of X bar, which happens to be same thing as sigma squared over my sample size. Whatever my sample size is, the standard deviation of X bar is going to be the standard, the variance of X over my sample size. Okay. We call that the standard error. Well, technically it's standard error squared because I'm still talking in variance terms. But the root of that would be the standard error of X bar. I'm going to call it the standard error to just say I'm talking about an estimator. It's just the standard deviation of my estimator. That's what a standard error is. Okay, so that's what it is. All right, so that'd be super nice, but again, I don't know that, right? I don't know that because I don't actually know what the true population is. If I knew what the true population variance is, I could just plug it in there, but I don't. So instead, I'll just use what I got. I'll use S squared over N. Okay, that's the next best thing. Yes.
So are those left two? Are those sigmas? Or those S?
These?
Yeah.
That's a sigma.
Oh, okay, those are sigmas.
Yeah.
Yeah,
These are your S's. Yes. Yep. Yeah, so this is the variance of X. This is the variance of X bar, which happens to be this. Okay. All right, so that's what we got. So I got these numbers. I got X bar, and I got S squared. Okay. So, and then I also got a number for, how many people got attacked by the shark. So in my survey, seems like 4% of people were attacked by a shark in the last month, which is not good. It's pretty high number of people. So let me talk about this S squared for a second, because I should probably define what that is. So S squared, we know how we usually calculate variances, right? So a variance, we would normally say, we would take all our xi's, we would subtract our X bars, and we would take the sum of those squares, and then, we would do 1 over n, right? But for S squared, I'm actually going to do 1 over n minus 1 times all of that. Yeah, so the reason I'm going to do that is because I could do the other way. I could do 1 over n, the sum of all my xi minus x bars squared, right? That makes sense to do. I'll call that some estimator like sigma hat squared, okay? Notice how these are pure Greek symbols. And when we're talking about estimators, we either change it into an English letter or we put a hat on it. Those are kind of the two most popular things to do. All right, so I'll call this sigma hat squared. But the problem is with sigma hat squared is that it's actually biased. Okay, so the expected to have an unbiased estimator, that would mean that the expected value of our estimator, I'm just going to put like an arbitrary theta for an estimator. Oh, sorry, theta hat. So the expected value of that estimator should be the true value, right? That is what an unbiased estimator is. However, there might be some bias. We could find the expected value of that parameter is actually the true value plus some bias, which is not good, right? So, I mean, we could easily solve this formula for bias to just say that, the bias is the expected value of the estimator minus the true value, right? That is what the bias is. But that's not good, right? Because when I'm taking a sample, I'm not really hitting what I want to hit. Now, it turns out that sigma hat squared is actually a consistent estimator, which is almost as good as being unbiased. It's not quite the same. Basically, if I have this distribution, this is the distribution of sigma hat squared, right? And let's say that mu is over here, but sigma hat squared is estimating what? That would be variance, huh? So let's say that the true variance is over here, okay? If I have a biased estimator, then the mean of my estimator, this is the distribution of my estimator, the mean is not going to be the true value, right? So that's bad, like it's biased towards this. We would call this downward biased. If the distribution was up here, it would be upward biased, okay? But I could have a consistent estimator, which means that as my sample size gets larger and larger, my distribution could change and it could become a little more like that, a little more like that. And as I have like really big ends, it could be like that. And look at that. Now, all of a sudden with a huge N, I'm actually centered around my true value, right? So that is what a consistent estimator is. Notice with a consistent estimator that as my sample size is larger and larger, then the distribution of that estimator, the bias goes to 0, and it actually completely converges on the true value, which means what else goes to 0? The variance, right? So both the bias and the variance go to 0 if I have a consistent estimator as n goes to infinity. So while sigma hat squared in this case is biased, it actually is consistent. And let's just see what that looks like right here. So if I were to take the expected value of sigma hat squared, okay, it would look like, and then I were to basically do that formula, it looked like this. It looked like n minus 1 over n sigma squared. What do I want this to be if it's unbiased? The expected value. What do I want the expected value to be if it's unbiased? I want it to be sigma squared. I want it to be the true value, right? But I got this thing right here. So that's too bad. Now I can split this up so it's easier to see the bias. So let's do some math here. So if it's n minus 1 over n sigma squared, that's the same thing as n over n sigma squared plus, minus 1 over n sigma squared. So what is the bias of sigma hat squared? Yeah, that right there. That is the bias. Yes?
What is the expected value of sigma hat squared n minus 1 over n? Like, where did that come from?
So I don't really want to do like the whole formula.
Oh, okay. That's okay.
but you could in theory. Basically, what you would do is you would take the expected value of that, and then you just chomp that bad boy. Yep, we're not going to do that. So yes, that's what you got. Now, look at this right here. So what happens as n goes to infinity? Bias goes to 0. So is this a consistent estimator? Ah, but it's a trick question because I just gave you the bias, right? Now I already told you it's a consistent estimator, so you're still right. But let's look at the variance, right? The variance is, let's see. The variance, as you all know, is that. That. Yep. So again, what happens is this, as n goes to infinity here, variance goes to 0, right? We know that because there's a greater power of n on the bottom than there is on the top. So you can look at these and you can say as n goes to infinity, those goes to 0. Therefore, this is an unbiased, or sorry, not unbiased. It's a consistent estimator. Okay, perfect. So that's bias and that's consistency. And the other term that kind of goes along with those is efficiency, which is always a relative term. So if one estimator is more efficient than another, then it has a lower variance. It turns out that sigma hat squared is more efficient than s squared. It does have a lower variance. However, we prefer s squared because it is unbiased. Okay, so that's why I'm using s squared in my sample, for all of those reasons. Okay, but now let's get down to the nitty gritty. So let's talk some confidence intervals. Okay, say I already said I have some x bar that I calculated, and it's somewhere on this distribution, but I have no idea where. So I'm going to create some kind of interval of confidence to say, like, okay, this is what I got, and I think, with this degree of confidence that the true value is in this interval. Okay, so I'm going to do that. So confidence interval, I always like to think of it as you're taking your estimator. This is how most confidence intervals work. Our estimator here is x bar, and you're going to plus or minus some number of standard errors of that estimator. I'm using z here because of the normal distribution, right? Z represents the normal distribution, and I know that this is normally distributed. Now, if the thing is that if I didn't have the population variance, which I pretty much never do, then actually I would be using this for the standard error of x bar, which we already covered. Okay, and so in that case, like, it would actually be t distributed. Okay, it would be t distributed with n minus 1 degrees of freedom. So I would take my x bar that I got, which is 5, and I would plus or minus some number of standard errors, right? This is the standard error that I would plug into there. And my t would come from whatever my confidence interval is. So if it's a 95% confidence interval, I would go to my t-chart. I would look at what the t value is for a 95% confidence interval, and I would plug that right in there. And those numbers would give me some interval with a small number down here and a big number up here. And I would say, okay, with 95% confidence, like, the true value is somewhere in here based off the value that I got. All right, makes sense for confidence intervals? That's how they work. Do they all work that way? Well, no. So there's one more, right? If we're talking about the variance, it's a little bit different because the variance has an interesting way it interacts with distribution. So the sample variance, in fact, your degrees of freedom times the sample variance over the true variance, it happens that that is chi-squared distributed with n minus 1 degrees of freedom. Okay, so it's not quite as clean as just the distribution for x bar. It requires like a little more work, right? So we got some chi-squared distribution right there. And so if I want an confidence interval for chi-squared, then I would find out where there is 90, let's say I want a 90% confidence interval. So chi-squared, I would look somewhere on my chi-squared chart, and I would get 90% right there. That would be 0.9. And then that would give me two chi-squared numbers. I'd have a lower chi-squared number, and I'd have a upper chi-squared number. Okay, that's good. That's good. Almost there. So then I would plug it into this formula. I would say that n minus 1 s squared over sigma squared equals, okay, so I would know that I would have one of those for my lower chi-squared value, but I would also know that I have one of those for my upper chi-squared value. All right, so are we done? We're almost done. Okay, now I just need to kind of rearrange this math so I can solve for sigma squared, because of what I'm actually interested in is some values for sigma squared. That's what I'm trying to estimate, right? So turns out we can just switch these, right, with a little math magic, and I get n minus 1 s squared over my lower chi-squared equals my first estimate for sigma squared, and then I do the same thing with the upper chi-squared, and I get my second estimate for sigma squared. I take these two numbers, and those are the numbers for my confidence interval for the variance. Okay, so that's how you would do a confidence interval for variance. Yes, another thing that you would do confidence interval for is beta 1. It's another Greek letter. To estimate it, we would put a hat on it, maybe, call it beta 1 hat. And we're going to cover that one a little bit later when we talk about regression. Any questions on confidence intervals, though, before we move on? Is that all pretty straightforward? Yes. Ah, yes, yes. Okay, let's talk about P. Let's talk about that a little bit. So in this distribution, it's funny because I actually have a 4% proportion of people who got attacked by a shark in the last month. So here's what we do with that. What would that distribution look like? Kind of distribution would the population? Yeah. Yep. The Bernoulli would get a 0, we get a 1. And for this one, let's just put these numbers in. We got most people did not get attacked by a shark, and 4% of people did. Okay, so that's P, right? So what would the distribution of P hat look like? Ooh, a tricky one. It is normal, yes. It will be normally distributed around what value? 0.04. Well, yeah, I mean, actually it would be around the true mean, but in this case, we're just going to say 0.04 is the true mean. Okay, it's not, but you get the idea, right? It's normally distributed around the true mean. So this is the distribution of P hat right here. Since it's normally distributed, confidence interval is pretty easy. We take our P hat and we plus or minus Z standard errors. And the standard error for P hat would be just like the rest of the standard errors, right? We have sigma squared over n. So it's going to be the variance of P hat over n. See how that works? Right, the variance of P over n. Okay. How do we find the variance of P hat? I didn't get that. Yeah.
Multiply
Boom. Yes. We take P hat, 1 minus P hat. Boom, you got a variance. And what is that? Correct. It's 0.0384. Yes. So there we go. We got a variance for P hat there. So we just plug that in. So we're going to take the root of 0.0384 over n, which in this case, I didn't tell you, I surveyed 500 people. Okay, take that over 500, and that is the standard error for P hat. All right, pretty simple stuff. Any more questions? Yeah.
To calculate the variance of P hat, you don't have to divide by 500.
Just to calculate the regular variance?
Yeah.
No, no.
Like sometimes for the population, you have to divide by.
So you are only doing that for the variance of your estimator. Yeah. Yeah. So, yes. And I know I probably made some mistaken notation here.
No, it's okay.
Uh,
Never understood.
I apologize, whatever that mistake is. But, yes.
Yeah, why is it all rooted? I mean, like the other one was just like s squared over n. So why is this one square root?
Sure, yeah, this is the variance right here. So that's the standard error squared. So you just take the variance over n.
On the other one,
Yeah.
but is s squared over n the standard error, or is that?
No, this is the standard error squared.
Okay, so when we put that into x bar plus or minus t, we would just root that as well.
Yes. Oh, so sorry. Yeah. Sorry that I did not make that clear. No, this is your standard error squared, so your actual standard error would be s over root n. Yeah. Good catch, yes. The proportions normally distributed, so we don't have to worry about t. We just go straight to the normal. Is that? Do you not believe me?
So it's just if they're like, oh, what's the interval? Oh, it's 0.4 plus or minus square root of 0.03 over 500. Not multiplied by anything.
Times z standard errors. So whatever your confidence interval is, I think a 95% confidence interval for z is 1.96, if I remember correctly. This would be 1.96 standard errors. Yeah. Was there another question?
Yeah.
Oh.
So the only way to figure out that's this towards the middle left of the board. The only way to find the variance of your means is to have the population variance. You can't do that with your sample variance. Only like variance of x bar is equal to the.
Yeah, so this is, like literally, this is the variance. This is how you would estimate the variance. And you're pretty much never going to have this, so if it's a sample, you're going to use this.
So, but you could figure out your variance of x bars using, like we can use our estimator and divide it by n.
Yeah. Yep, you're just plugging in s right there. Yeah. Another question. Yeah.
Can you just run down again? So like when we use z versus t versus
Yeah, so chi-square variance estimation. If you're estimating a variance, then this is going to be chi-square distributed. That's what you're going to need to use. Yep, this right here. And I mean, unless you want to kind of skip the math and just be like, oh, I know that I'm going to need that over my chi-squared values. You do that too. Yeah. So z, if you have the population variance, then you can actually just go straight to the standard normal and use z's. If you do not have the population variance and you're using s squared, then your x bars are t distributed with n minus 1 degrees of freedom. So you can use that t distribution. Now, when your sample size is big enough, when your sample size is like over 30, the t distribution looks like pretty much exactly like a normal distribution. So like if your sample size is bigger than like 30, then you can just use the standard normal if you want. It's going to be like exactly the same numbers. So does that answer your question? Okay, perfect. P, always normal. Yeah. What's that? The Bernoulli, so that's P, right? So this is what P would look like its regular distribution, but your estimator is going to be normally distributed around the true value. Yeah, it's proportions is what P stands for. All right, confidence intervals. Any last questions? Okay, we are moving on. Oh, don't erase that. Don't erase that. Okay, so H-tests. Let's start at the very beginning. A very good place to start. When you read, you begin with ABC. When you test, you begin with H. No.
HA.
You're supposed to sing it.
No hypothesis.
H null. Okay, never mind. Never mind.
Wait, there's a song.
Okay, H null.
Singing sound
Solo.
music.
What is my null hypothesis? Okay, that's sing what?
Sing
Sing.
sound of music for us, Stephen.
I just did, but you guys didn't sing it back.
We were wanting to hear you sing.
Wait, give us one more chance. Grace.
When you test, you begin with H null. H null. Yes, very good, class. Okay. So, these are the ingredients for a hypothesis test. Okay. You start with what is my null hypothesis? What am I testing? I want to test a null hypothesis. Okay, let me see. What do I want to test here? Let's test. I think that. Oh man, why did I erase this, man? Come on, bro. Okay. I think that the true p is actually 2%. I think like in reality, it's actually 2% of the population attacked by a shark. I just got 4%. You know, it's just a weird sample. Okay. So my H null is that p, and our H nulls always include. Okay, I know that p is not a Greek letter, guys. All right, I'm breaking the rule here. But that's just how it is. I'm sorry. Okay, but we're always going to use the unknown here. Your H null is always going to be about a population parameter. Okay, so I'm going to, the null hypothesis is that p, the true value, is 0.02. And then I need an alternative hypothesis. In this case, I could do p is greater than 0.02. So if I reject the null hypothesis, then this is the alternative hypothesis. That's the conclusion. This is called a one-tailed test, because if I'm looking at a distribution and I have some value, I'm going to be looking at one tail. What would a two-tailed test look like? Yeah, p does not equal 0.02, in which case, so I have some alpha here, right? Some significance level I want to test. So let's say that's the 5% significance level. So, right, at 5%, if my p-value is less than 5%, I'm going to reject it. So in the one-tailed test example, this probability is 0.05. But if it were a two-tailed test, then actually the sum of these two probabilities, that would be 0.05. So a two-tailed test would actually have a different conclusion sometimes than a one-tailed test. Yes.
Would it make any sense for your null hypothesis to be greater than 0.2? Like to not be the one that's equal, but the one that's like not this value greater than 0.02, and then the alternative hypothesis is
Oh, for your null to be that?
or does the null always have to be set?
Yeah, I mean, what we're really saying with this is kind of a shorthand for p is less than or equal to 0.02. It means the same thing. We just tend to say p equals 0.02 because like that's the most extreme thing that it can be. So yeah, does that answer your question?
Yeah,
So,
I will have a follow-up question about that.
okay, another question? Yeah.
So when you said like the two-tail, the probability has to have the 0.05, so that changes your critical value.
Yes, it does. Yeah. Yes, it does. And to recap the terminology there really quick, so in a hypothesis test, you have, before you even start, you have your null, you have your alpha, your alpha, also known as your significance level, and you have your alternative hypothesis. So you're basically saying like, here is the assumption, here is the null assumption that this is the distribution and that 0.02 is at the center. Okay, this is the assumption that we are testing. We're testing the assumption of the distribution around 0.02. And if this assumption holds, then we're going to draw this distribution and we get 0.04 out here. Okay, so, sorry, wait, I'm moving too fast. Okay, we got 0.02, right? and our alpha is 0.05. So if we're doing a one-tailed test, we're going to reject it at some level right here that we'll call the critical value. Okay, and so this whole area, that is alpha. Okay, that is our significance level. This region is our rejection region, and it's going to be past some critical value. Now, when we take our test, we're going to get some test statistic value. It might be below it, it might be in front of it. Put the test statistic value right there. Okay, so that's what we get for our test statistic. We'll just plug this in, 0.04. Okay, and this probability right here, this region, is the p-value. Okay, the p-value represents, like, okay, I'm assuming that this is the distribution, it's around 0.02. This is the probability that I would observe a test statistic, at least this extreme, assuming that this distribution is true, right? So if that probability is like really low, then I'm going to reject that assumption. I'm going to be like, okay, this probability is like super small, so I'm going to reject that this is actually true. Like, it can't be centered around 0.02.
So when we're gonna solve this, we're gonna standardize it. We are gonna plug in mu as 0.02, right? And x bar is 0.04. Is that why? Like, that's where we're getting the assumption that we're working with this graph that the null hypothesis is true, because we plugged in the values of the null hypothesis when we standardized it. Does that make sense?
Yep. So this test would look like what you're testing minus what you're assuming is over the standard error of what you're testing. Okay. So plugging all these in, that would mean we have 0.04 minus 0.02 over the standard error of p hat, which is going to be the variance of p hat over n. So standard error, or sorry, the root of that. So there's the variance, and our n is 500. Okay, so from this, we're going to get some value that's going to represent this part on our graph. Someone want to calculate that really quick? See what we get. Yeah.
I actually have a question. I was doing one of the practice exams, and there was like a certain question that was proportions. I had like the standard error calculated with p hat, and another version calculated with p, and it said either was right.
Yeah, it's the same thing as if you have the true population. Like if you have,
Like we knew the true population.
yeah.
Does it not matter which one you use?
So if you have the true population, always plug that in. That's good. That's good information.
But it doesn't really change the answer.
Yeah, it's just if you're using the estimator, it's going to be a less accurate estimate.
Okay.
So yeah, you can use p in place of p hat when you're doing calculations.
Okay.
I think I got your answer. I think it's 0.72. Not what I got.
What'd you get?
2.28.
Okay. Don't trust mine. I
Okay.
think I'll that.
Let's see. Okay, so if we plug this in, we got 2.28. Then what would that mean? What would we need to do now? We go to the table, right? We see what the great Z table says. And what does the great Z table say that this this probability is here? Z table, because of this P. Yeah. What's that? 0.9887. Someone else get that? Well, it can't be over 1. So what'd you get? 0.9887? Yeah. So 1 minus that would be 0.0113. Okay, 0.0113.
Oh, that's the p-value.
Yep.
Oh.
Okay, so with a p-value of 0.0113, then what do we conclude? Correct. All right. This is definitely smaller than 0.05, so we're going to reject that null hypothesis. Yep. I can relate to null hypothesis a lot. How much I get rejected. Yes, Margot.
Alright, if you were doing a Bernoulli distribution and therefore you can then would your p-value not be one-sided percentage? Where would you find that?
Yeah, you would find the equivalent thing on a t-table, which t-tables are a little bit harder to read for that because they don't have as many exact values. So you just give your best estimate.
But that would be how you would find.
Yeah, with your degrees of freedom. Yep. Okay, so that is a hypothesis test that we would conclude. So we'd say, yeah, it's definitely, we're going to say it's more than 2%. All right, so that's what we've got for our hypothesis test. So we understand that like p-value being less than alpha is the same thing as our critical value being let me make sure I say this right, is the same thing as our test statistic being more extreme than our critical value. So those are equivalent. You can do it either way. So I could do this by comparing p-value to alpha, where p-value is less than alpha, or I could do it with like straight up, I could get a critical value and I could compare that to my test statistic. And if my test statistic is more extreme than my critical value, I would also reject. Yeah.
There like
No relation. The P and V value, I'm pretty sure, is probability. The P in Bernoulli would be proportions. Yeah. I get that. I get that. That's just what they named it.
I have a question about H-tests.
Okay.
So coming up with a hypothesis the thing that you are like think to prove or the thing you prefer to prove.
Yeah, you could look at it that way. Yeah. So basically your null, yeah, you are seeing, the point of a hypothesis test is to see if your data provides evidence to reject the null. Yeah, I mean, it's what you're assuming unless your data is extreme enough to reject it. Yeah, yes. Good. Any more hypothesis test related questions? All right.
Oh wait.
Oh, yes.
So let's just theoretically say that we were doing two-sided.
Yeah, let's do two-sided. So that would be that P is not equal to 0.02.
What would change?
So this right here would change, right? So you'd still do these same calculations. You'd still end up with 2.28, but then look at your Z table. What would that change into?
Or it should get added up, so 0.05 on both sides.
Yeah, so you get 0.025 on each side. So they would add up to 0.05. Mm-hmm. Yeah, so
wanting the critical value?
we want,
What were you just asking?
you got 2.28, and you want to find with two, wait. Doing this right?
We divide that down by two.
Wait.
What do we divide?
No, yeah, you'd still get 2.28. Am I a crazy person? Yeah, let me see your Z table.
The critical value is 1.96, I think.
That's what I just got.
How'd you get that?
Just find
Like going
0.025 in the
Yeah.
middle of your z
Finding it in
and
the
see what
table
the
and
critical
seeing what it-
values
You
are.
find 0.025.
0.025.
Because you want both sides to add up. And a z table shows everything up to just the z
What
table
did I
shows
get?
everything.
I think I got
from
negative
one to
1.96.
here. So if you want 0.2, 2.5%.
Oh, point-
Oh,
oh,
yeah,
yeah,
that
yeah,
makes sense.
That makes sense. That's the number that always.
Okay. Oh,
That makes sense.
So I look for half of the value that I'm doing
You guys broke me. Hold up.
I'm not sure I'm right, so but I just looked at this and I found 0.02. Like in the table. Yeah.
That makes sense.
So you kind of do the opposite.
So if they give you, they'll
Oh
give you
yeah.
alpha value,
I think we just
basically
broke
the
stats.
Let me look at this.
Says that the
So
alpha value is
2.28.
when we're doing just one-sided, the alpha was the shaded graphs. But it's a two-sided test. The alpha now knows the
Okay, okay.
top and bottom.
I think this is the problem. Okay. So you got what? Like initially you got 0.0113, yeah? Okay, so whoever said this, I think someone said this. You just, or maybe it was you that said this, Margo. You just multiply that by 2. Okay? So what is that? 0.0226.
No, don't you multiply alpha by 2?
Wait, why would you?
So alpha is always going to stay the same.
That's what the test is.
You
So
would divide
two-tailed
alpha by
test. Oh yeah, that's right. You divide alpha.
Yeah. So now 0.0226 is your probability because you have this over here and you have this over here. Yeah, so you'll actually do the exact same thing for the table that you do as the two-tailed test. So you look up 2.28, but the interpretation is different. So for the one-tailed test, you have 2.28 gives you 0.0113, which means 0.0113 is this shaded area. We all good with that? Okay, now for a two-tailed test, you need that shaded area on both sides. So 0.0113 is on both sides. Therefore, your total probability is 0.0226.
Oh, the p-value is 0.
Yes, this is the p-value. Yeah.
So if it asks us to do two-sided, we should just multiply the p-value by 2.
Yep.
And then compare that to the alpha. Same thing.
Yep.
So we'd still reject it.
Yeah. Now if your alpha was 0.02, that would have made a difference.
You would fail to reject.
Yeah. So okay.
Like in words, our null hypothesis in this sense is saying that the probability is either equal to or less than the percent that we have a shark attack if we.
Wait. Okay. Say what you said again.
What is the null hypothesis in the sense
Null hypothesis. I think that the population of people that get attacked by a shark in a month is 2%. So a two-tailed test alternative would say it's different than 2%. Yeah.
So you mentioned like this is the same as like saying the test statistic is more extreme than critical value. So you can solve it that way too, right?
Probably.
Like
Yeah.
show that.
So I didn't compute the critical value here, but you could. So
You just find where alpha, that number on the normal
yeah.
distributed table.
So your alpha, if your alpha was 0.05 or 0.02, you would look on your z table for what number that correlates to. Yeah, and then whatever number that is, that's your critical value. That's what you're comparing against your test statistic.
2.28.
Yep.
Okay.
Yeah.
You can solve it either way.
Yep, they should. I mean, I would encourage you to do both and check your answers by doing that. Yeah.
This is not related to hypothesis tests.
Okay. I'll take Margot's question first, and then we'll circle back.
Okay, so if we do that, we like look on this part
Uh huh.
of the paper.
Yep.
And we're like, oh, where does it say 0.05?
Exactly.
We're like, oh, look, it's way over. How did the segment go? It's something. And then you're like, what number does that correlate to? Negative, blah, 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 blah. And then you're like, is that more or less than 2.28? Yes.
Yeah. So just make sure you know where on the graph you are.
Okay.
It's more or less extreme. Okay. So if you maybe you look at your z table and you're set up in such a way that you get this value over here, right? But you're actually looking at this over here.
Okay. So like
Does that make sense?
the table is at -1.4. That means it's less than 2.28, which means you failed to reject it.
Not exactly, because you're looking for the value. Well, for the two-sided, but for the one-sided, you're looking. If we're saying that our alternate hypothesis that it's greater, you'd be looking for it on the right side, so which would mean that your critical value has to be positive. You're looking for a value that's less than your critical value.
Yeah, and so if your alpha was 0.05 and you're doing a two-tailed, if your alpha is 0.05 or 0.02, and you're doing a two-tailed test, then when you're looking in your chart, you would look for half of alpha.
Okay, but if I'm doing one tail, then I get -1.64.
Then yeah, you just compare that to your. Yep. Yes.
So, as a rough estimate of maybe a low there are like 20 to 30 equations for this unit. Do you have a list anywhere for those, or just like
Yeah, I mean, I would know, like, I like to think in general terms. So in general terms, I think confidence interval, okay, that's my estimator plus or minus whatever my distribution stat is of standard errors. Okay, and this is gonna, this is gonna apply to a few different things. Maybe this is normally distributed, maybe it's t-distributed, but then you're gonna take the standard error. So I would know how to get your standard errors of each of your estimators. And I mean, you guys know how to find t's and z's, but yeah, I think standard errors are, like, if you know that, you can know confidence intervals. We went over chi-squared and how that distribution works, so that would be a good thing to know. So for confidence intervals, like, this is how I like to think, and we went over how chi-squared is different than that, but you guys will get that after going over chi-squared. But and then I think in general terms of, like, the thing I'm estimating minus, I mean, the general, like, standardizing formula, right? X bar minus mu over sigma of X bar is how I would standardize X bar. Where this is your standard deviation of what you're estimating, and this is the true value. So that's going to be the construction for every hypothesis test you do. It's just the standard errors are going to be different, and because, like, what you're estimating is going to be different.
Okay, is that the same thing?
Yeah, so this is the standard deviation of what you're estimating. Right, since it's X bar, this is the standard error of X bar. Standard error, standard deviation, same thing. Yeah. Okay, perfect. Any more hypothesis test questions? Okay. Okay, now let's take it back. Let's take it back. All right. Oh no, my distribution of X bars. So sad. Oh, whatever. Just like having that there. Okay, so let's talk. If I had, we're going to talk about not this survey right now because for reasons, but let's say I had a sample that I took and it had some, I scatter plotted it in Stata and it looked like that, right? Now, I would like to be able to look at this and predict based on the value of x. I would love to predict like what y would be, right? There's a lot of value to that. So it would be nice to run a line through this, okay? So I need some kind of way to run a line through that. And I know it looked really easy on the board because I just drew it, through the dots, but I want the line of best fit. And mathematically, when you're working with a bunch of values, that requires something more than just drawing a line. So the value, or the method we use, is called ordinary least squares. The reason it's called ordinary least squares, I'm not going to go over the ordinary part. You can figure that out in 388. But basically, least squares, because what we're doing here is for each value, you can think of each value here as having a part of it that will be explained by your line, and another part of it that is left over or residual, okay? So part of it is explained, part of it is residual. I'm breaking it up into those two parts. Ordinary least squares means that mathematically, if we want the line that best fits this data, and we're going to take all of these residuals, we're going to square them, sum them all up, and we want that to be the smallest value we can possibly have it be. So what we're doing is we're minimizing the sum of all of our squared residuals. I'll call those epsilon I hats, because you can think of epsilon as being like some true error of a true line, like beta 1 is true, but then epsilon hat is like just what I got from my sample. Okay, so anyway, we're taking all of these residuals, squaring them, summing them up, and we want that to be the smallest value possible. That is what OLS is, ordinary least squares. That's how we get these lines. Now, you guys all know the equation of a line. It's y equals mx plus b. In econometrics, we like to call the b beta. We like to call lots of things beta. So we call the slope beta 1. Sorry, we call the intercept beta naught. We call the slope beta 1, and we write it like that. Okay, that's just the equation of a line, just using betas instead of m and b, right? But for each of these, you can think of the y for each of these different values as being that line, but plus like some varying error, okay, that we'll call epsilon. So that's kind of what we're representing right here. We have the part explained by our line, which is this right here, and then we have some unexplained part, right? That's our error term, okay? So with OLS, what we're doing is we're doing a y hat, right? We're predicting our values with beta naught plus beta 1 x hat. All right, these are just put hats on these because technically they're estimators and everything. So this is our line that we're drawing. This line is represented with beta naught plus beta 1 x, okay? And each value has some error term with it as well. Now, the sum of the squared residuals, I'm gonna abbreviate like SSR, right? The residuals come from, if you were to solve this equation to find out how to get a residual, then what would be the equation for a residual? Yeah, or equivalently, I could even write y minus y hat, right? The actual value minus the predicted value. This actual value of the dot minus what my line predicts that it will be, okay? So this is the same thing as minimizing my yi minus y hat I squared, right? I'll call that the sum of my squared residuals, all right? So saying that some of it is explained, saying that some of it is residual, I could say, all right, well, the total would be, the sum of the squared residuals and the sum of everything that's explained, sum of squares explained, and that would be like a total, right? I'll call that SST, the total of all of that. All right, makes sense. If I did some little math and divided all this by SST, then I would basically get the proportion of the total that is the residuals plus the proportion of it that is explained by my line equals 1, right? Okay, so I have some proportion that's explained by my line, and I have some proportion that's residual, okay? So here's the thing, is that solving this for the proportion that's explained by my line, all right, this right here, the portion that's explained by my line, I'm going to call that r squared, okay? R squared is the amount of the variance in this data that is explained by my line, all right? And R squared, we call that because it's actually your correlation coefficient squared, which is rho. So it's actually rho squared, all right? So if you're asked to predict or asked to calculate R squared and you're given rho, square rho. That is your R squared, okay? So that's 1 minus the proportion of this that is residuals, the sum of your squared residuals. All right, so that is the intuition under regression. That is how regression mathematically works. Now, if I wanted to know the formulas for beta naught and beta 1, well, beta naught's not too complicated. I could say, look, if I know that the average y is just going to be, beta naught plus beta 1 times my average x, well, I can just solve that for beta naught. Then look at that, right? My beta naught's going to be my average y minus beta 1 times my average x. That's not too bad, okay? Beta 1, it's got a little bit of a different formula. The one that he taught you, which is the one that I will teach, which is your correlation coefficient, sigma y over sigma x. Okay, so you get beta 1, rho times sigma y over sigma x. Plug that bad boy in here, you can get beta naught as well. And those are your estimators. Technically, those would be hats, but you get the gist, right? So that's how those work. So that's how you get those. And if I were to ask for a confidence interval, oh yes, sorry, go ahead.
Beta 1, so it's sigma y, sigma x, but would that work for like sy, sx?
Yeah, I mean, you would, from your sample,
Don't have sigma y, sigma x, right?
yeah, practically from your sample, you would plug sy and sx in here. Yeah, I mean, yeah, you're estimating beta hat 1. So like beta 1 is this, and beta hat 1 would be your sy over sx.
Okay.
Yeah.
For your error term, when you're subtracting the real value from the predicted value, do you also do 1 over n minus 2?
Yeah, we'll talk about that. Talk about the 1 over n minus 2. Yeah, let's talk about that right now. Okay, so basically that comes into play at least, maybe just remembering another place, but when you are wanting to know the standard errors for beta hat 1. Yeah, so this is kind of like this formula, I'm not gonna lie, this is like my least favorite. But first, the first thing you want to know is you want to know the sample variance of your error term. So the sample variance of your error term is going to be 1 over n minus k minus 1 times the sum of your squared residuals. I could have written SSR here. I could have written, how do you calculate E? What's the formula for E? Right? I could have written that there, right? Did you guys get that this is, the sum of your squared residuals times 1 over n minus k minus 1. And n, we know what n is. K I write here because, yeah, I know. If you had a, if you had like a multiple regression with multiple x's, k would be how many x's are in your regression. So, so since you guys since you guys are working with, only one x, it's going to be n minus 1 minus 1. That's why it's n minus 2. Okay. So when you're doing regression, it's how many x's are in your regression are going to be your degrees of freedom down there. Okay. Yeah.
Is that SE as in standard error or as in sample?
This is the sample sigma.
No, sorry, not sample. Yeah, sample.
This right here is the sample variance of your epsilons. Yes. Well, okay, this is why you need that, because the standard error of beta hat 1 is the sample variance of your epsilons over, let me see if I get this right, the sum of your xi minus x bar squared, or in other words, not just the variance of your x's. No, because you need a 1 over something there. Yeah, so let me check that this is right, because I always get this formula wrong. Yep, okay. So that is it's actually your standard error squared. And writing all of these as variances. Sorry, guys. So, but it's going to be the s squared of your epsilons over the sum of your xi minus x bar squared. Therefore, the standard error of beta hat 1 is going to be the root of that. Okay? Yes, this is the standard error of beta hat 1. So if you're calculating a confidence interval for beta hat 1, then we know how to calculate confidence intervals, right? This is a sum, capital sigma. Capital sigma is what I'll have my kids call me. Yes, capital sigma. Yes. So we know how to do confidence intervals. We would have beta hat 1 plus or minus. And then how is this distributed again? It's distributed, I think it's t distributed. Yeah, t n minus 2, thank you. So t standard errors. Okay, so you take your beta hat 1, you plus or minus t standard errors, t with n minus 2 degrees of freedom, because it's a regression with one x variable. Okay, and that is your confidence interval. And if you want to hypothesis test, then you're going to follow the classic x minus mu over sigma notation. Like that. Plug in appropriately with the standard error of beta hat 1. Your beta is going to come from your h null. So that's how you do that. Okay. Your t is going to come from your confidence interval. Or sorry, you're talking about this? So yeah, this is t distributed with n minus 1, n minus 2 degrees of freedom. What, this? This is for hypothesis testing. This is just a classic, like x minus mu over sigma notation. Yeah, I'm changing some stuff, but you guys get it's your estimator minus the true thing over your standard error, standard deviation every time. Yeah, I mean, he's probably only going to ask you to do that for beta 1 hat. Maybe he'll do it for the intercept, but yeah, I don't think you know the standard error for your intercept. So, yeah.
I don't think we do either.
Okay.
Yeah.
When we're doing your regression formula, I know how you like add the error term on the end. On the test, if you were to give us like all that and we have to like find the error term and then we have to like go through some regression, we also add the error term to our.
No, because it's your prediction, right? So your prediction is just going to be beta hat naught plus beta hat 1x.
On average, epsilon is 0.
It's true. You don't have to know that, but
Oh, that is true.
Yeah.
Oh, yeah. Because the line, by definition.
So this is your line right here. So when you're making predictions,
Why do we care about the error?
you're identifying points on your line
It averages zero.
on average. Like none of these is zero.
Oh.
Like all of these
like
have
you a massive
residuals.
Well, yeah, it just
I
shows
mean,
how spread out your data is.
yeah. So your R squared, your R squared is going to be like, I'll give you a difference between like a good R squared and a bad R squared. So like,
Your R squared is directly correlated with your size of the E, right? Bigger R squared means smaller E.
not smaller E, but smaller proportion of your residuals compared to the proportion of what's explained by your line. So I'll show you like, if you have some data like this, you run a line through it, like you're gonna get a pretty good R squared from that data, right? If you have some data like this, and you run a line through it, like you get the same line, but you're gonna get a worse R squared.
And the error term on the second one would be
Your residuals would be bigger. Yes, and the sum of your squared residuals would be bigger. Forget the average of zero thing. Don't.
But when you're using values to predict the Y, don't add the E. Don't add the error.
Yeah, you're just talking about points on your line.
Be above or below. Like you never know which error to add.
So this is like plus or minus.
Yeah, you wouldn't know.
Oh, that's why you do a confidence interval.
Yeah, you're just saying, hey, you tell me you consume 7 ounces of ice cream a month. I predict that your chances of being attacked by a shark are that. Okay.
These two equations I got lost that are below your first little graph.
Mhm.
What are both of those again?
Yeah, so this is the standard error of your beta hat 1. So the standard error of your beta hat 1 is this, and this comes from this equation right here. This is the sample variance of your epsilons.
So the top one is the sample variance of our epsilon or our error terms, and then the
Yep.
bottom one is the standard error of our beta one.
Yep. Yippers. Okay. So yeah, if you were asked a question like, this is pretty much always how it's asked, and people are always like, what the heck is this talking about? If it says something like, oh, what fraction of the variance in the population, or what fraction of the variance in the sample is explained by, yeah, I forget how these questions are worded, but if you have any question that starts with what fraction of the variance, like that is an R squared question. So what is R squared? You probably have already been given your correlation coefficient. So pretty much always how those questions are answered is you just square your correlation coefficient. So yeah, so it's what proportion of your data, the variance in your data, is explained by your line. Variation. Okay. Yeah, so what proportion of this variation in your data is explained by this line? That's your R squared. Okay, sweet. So that is, I mean, those are really like the main topics. We'll do one more thing. Let's say that I sampled separate survey. I only got 50 people this time. These people are all gamers, okay? And I found out that for gamers, I got an X bar, meaning ice cream consumption. They consume 4 ounces of ice cream a month. I didn't actually ask the shark question. That's all I got. That's all I got. I'm going to assume it has the same variance as the other people, because if we don't assume it has the same variance, then stuff gets real. So, and we don't want that. We don't want the math that's involved with that. So here's what we've got right here. okay, an x bar of 4, and I want to run some kind of hypothesis test that's meaningfully different, that gamers have a meaningfully different amount of ice cream consumption than the rest of the people that I sampled my ice cream. Okay, so my H null would be that basically the difference between, these are always in terms of population parameters. So it would be that mu1 minus mu2 equals 0. That's how I would write the difference between these is nothing. There's no difference. They're the same. That's how I'd write that. My alternative hypothesis would be that mu1 minus mu2 is more than 0. Okay, I'll do a one-tailed test for this. I could do a two-tailed test. All right. So then I would have the same kind of setup for my hypothesis, but I would just set it up with my parameter being this difference. So in other words, I'd have the difference, and my estimator for the difference is x bar 1 minus x bar 2. I'd subtract the true value, what I'm estimating is that parameter, mu1 minus mu2. I would put it over the variance, or the standard error, sorry, of this difference. And the standard error for that difference would be the square root of the variance, yes? So the variance of this difference would be the variance of x bar 1 minus x bar 2, which is what? Right, plus 2 covariance. Now this covariance stuff, this also gets like really mathy, and I do not think you guys will ever be asked that. So for this particular sample, we actually can't calculate it because these are obviously correlated. But basically, if you're doing a difference in means, you would take the variance of these, which would end up assuming independence, that it's the variance of x bar 1 plus the variance of x bar 2 root that. And you know the variance of these guys because this is just your standard errors squared. So if you plugged in your standard errors squared, you would get your s squared over n. So let's just plug that in because we're assuming the same variance. So it'd be 9 over 500 plus 9 over 50. Okay, so this is how you would perform a difference in means hypothesis test. Your degrees of freedom would be, instead of n minus 1, it would be n minus 2. Yeah, yep. So, and by n, I mean the total sample size. So you would be 500 plus 50 minus 2, 548. That would be your degrees of freedom. Yeah.
I think when I was saying class, we just always assume it's normal. I think he said that when we're doing difference in means, we just assume it's normal.
Okay.
So even if whether you have population or sample variances in your denominator, we just assume it's normal.
Okay. Roll with that. I like it.
Yes.
Just because it's usually big, is it
Yeah, I think it was really, really messy. Try to do it.
Yeah, this kind of stuff can get messy quick unless you have a lot of assumptions. So, yeah. Okay, so that is like the material that you guys have covered in this unit. Yeah. So it like I know like you cover a lot of different things and they seem really different, but like if you just remember like this is what a confidence interval looks like, this is what a hypothesis test looks like, and then you just need to know like your standard errors. Like you can't avoid that. Like unfortunately, like you can't avoid this. You just got to know that. Oh, that'd be sick. Yeah, if he gives you that, yeah, that'd rock.
Yeah, and the other ones are kind of similar to that one.
Yeah, this is the most confusing one. The other standard errors, like they all make sense.
The denominator
So,
is equivalent to squared over.
what do you mean?
The xi minus x bar squared is the same.
XX squared?
But it's times n minus 1, right? 1 over n minus 1.
Yeah, I have written down.
Oh no.
There is somewhere in there, like, because the way he wrote it out.
That's the difference of means, right? Got x1.
No, he's not talking about
It's
difference in means.
so it's SE squared over n minus 1 squared. That was where we solved for some. N minus 1.
Oh, okay. So we gave you a different formula for this? Okay.
Yeah, it's
I
like
think it was the
same thing,
variance of
but
the error
it's-
terms over the sample variance of x times n minus 1.
Okay. All right. So use that if you want to.
Yes.
Yes.
Do you think you could just like write down formulas for this?
I would love that.
Sure. Yeah. So eliminate some space on the board here. So we got some help over here. Okay. X bar. X bar has this kind of distribution with this as its standard error, or it has a t distribution with that as the standard error. Okay. Let's see. If we're talking about variance estimation, then you don't like there's not a standard error for variance estimation, but like the formula for chi-squared distribution is that. Okay, so if you're ever doing variance estimation, you will use this formula right here. Okay, so unfortunately I just erased beta hat 1, that's annoying. Beta hat 1, you have to know this, the sample variance of your epsilons, which is 1 over n minus 2, the sum of your squared residuals. Yeah, and then once you have that, you plug it in for your standard error of beta hat 1, which is the sample variance of your epsilons over the sum of your xi minus x bar squared. The root of that, again, these standard errors, sorry, are all roots. Okay.
What's the difference between those two on the left? The t distribution and the.
If you have your population,
Oh, that's just if you have. Oh, worse if you have your sample.
yeah, if you have your population, you can go straight to a normal distribution. If you have a sample, you got to go to a t distribution. Okay, that's for x bar. Am I missing anything? P is normally distributed. The standard error looks exactly the same as x bar, but I can
You could write that down.
write it. I'll write it next to x bar. It is the I'll write it like this. It's the variance of P hat over n. Yeah, or the variance, same thing as the variance of P over n. Actually, just use that, yeah. So
Square root.
square root, thank you. I wrote it like that, like I could have written P times 1 minus P over n. I just really don't want you guys to think it's a different formula, because it's like not, like this is a variance over n, this is a variance over n, this is a variance over n. Like they're all, see how they're all, for x bar and for P, yes. For beta 1, like I don't know where that comes from.
Population variance. You go for a standard.
Mhm.
We have our sample variance.
Yep, exactly. Okay, I think that's it, unless I'm missing any more standard errors. Yeah.
Might be a dumb question, but for the chi-square one, why, like, do we have to have both the sample and the population to be able to use that?
Yeah, so basically what this ends up looking like is you're gonna get a couple chi-squared values based on what you want your confidence interval to be, and you're gonna use your your chi-squared values. Like this area, this is going to be like, 0.95, something like that. So you take your two chi-squares, you plug them in here, and you get that for each of them. And then you're just going to solve for sigma squared. So if you want, you can just skip just do this over chi-squared for each of your chi-squared values. And that's going to give you two ends of your confidence interval for your variance.
Because we're not going to solve and find out what the population variance is.
No, yeah. So this is these are the ends of your confidence interval for your variance. Yeah.
I'm just curious about the beta formula. I feel like you had one where it was like in the denominator it was sigma of the epsilon squared over n minus 1 s of x.
Yeah. So what's the other formula you guys have?
So the denominator
Beta 1 n minus
n
1.
minus 1.
N minus
variance of
1.
x. Sample variance of x.
Sample variance of x.
Yeah.
Is that it?
Yeah.
Oh.
For your denominator.
Yeah.
And that's
underneath
t
beta.
distributed with.
Yeah.
That's the one we assume that it's normal.
That was normal.
Oh,
But this one he'll give us on the test.
Actually, no. This one can be t. Actually, t if it's s is n if it's.
Oh.
T if it's s is n. Yeah, that's what I wrote down.
Yeah, that is true. I got it down too, actually.
So t will be for samples, n will be for population.
Yeah. I mean, if you always default to t and you realize you have oh, I don't have a sample, then you're not going to be able to get degrees of freedom. Thus, you'll be like, oh, I should be using the population that he gave me. So, but yes. Okay. N minus 2. Yeah.
Yeah, if the variance of the error terms, if it's the sample variance, then it's t distributed. If it's population variance of the error terms, then it's just we assume it's normal.
Yeah.
And the normal one he'll give us on the test.
Okay. Perfect. Okay. At this point, we're gonna go into exam. Any exam questions you guys want to go over, unless you guys have any other general questions right now, or things that you want to address more.
Like just a field marshal question.
General questions. Okay. So are there any topics? This is kind of what I noticed. If I were to just make something really basic of what I saw on the exams, it would be properties of estimators. It would be confidence intervals, and and hypothesis tests. It would be regression stuff. And then this kind of falls under hypothesis tests, but just making sure you understand, p-values, critical values, alpha, all that good stuff. So, I mean, those are really the main things that I noticed that were on the practice tests. There wasn't anything really that stuck out not involved in those categories. Are there any of these things that you guys feel kind of weak on that you want to do a problem on? Yeah.
Go over
Correcting bias. Correcting bias. Do you have an example or question? So on exam B, there is he asks you to derive a certain bias, and he also asks for an unbiased estimator. Do you have a particular question you want to go over for Mr. Pixton?
Yeah. Okay. Exam B question 4D. Oh, but it's gonna have us like run through a regression, and then it says propose an unbiased estimator, beta hat, the difference, beta equals for beta 1b minus beta 1 n and coefficients for two subpopulations so that the bias is
Propose an unbiased estimator for the difference and show that the bias is 0.
oh, but it gives you all this.
Okay, I'm kind of confused. The unbiased estimator is literally just what he gives you. Like straight up, if I'm reading this problem right, like he says, propose an unbiased estimator for the difference beta equals beta 1g minus beta 1 ng. He says propose an unbiased estimator, but if you choose an estimator as just like the exact same thing, run the expected value of that, then it'll turn out that it is, yeah. Yeah, so this is basically like, this is a one-line thing. So the expected value, this is what he says. And this is attached to the rest of the problem, so I would have to read the rest of the problem to go through it. But basically, he takes the expected value, which is the expected value of beta 1 hat g minus the expected value of beta 1 hat ng. No, we're just yeah, to show it's unbiased, we just take the expected value and show that it's the true value. And we're looking at, we know that beta 1g minus beta 1 ng equals theta, so the bias is 0. So, I mean, so you're going to have the expected value of each of these. The expected value of beta 1 hat g is beta 1g. The expected value of beta hat 1 ng is beta 1 ng. And we know that that is theta. Yeah.
So how do you prove that the bias of theta hat is 0? Like, is it that?
I mean, I think this would be sufficient. You showed the expected value is this. If you wanna like literally derive the bias is the expected value minus the true value, which is theta minus theta equals 0. So
I like it.
yeah, it's a very easy unbiased estimator. You just literally use what he gave you. Okay. Any other questions that you guys want to go over? I'm sorry I erased the topics, but confidence intervals, H-tests, regression, estimator properties.
You do the later parts of this question.
Like keep going.
I found like part D. No, C or I think C and D. The whole question. Honestly, yeah.
So, okay, if you guys want to do this question, I just have a question about if he's ever talked to you about this notation. If you look at the table in question 4, one of the values is SXX. Has he ever talked to you guys about that?
I think it's just S of X squared. S, the variance of X squared.
Oh, your sample variance?
Yeah.
Okay.
I think.
All right, I buy it. No. Nope. Okay, a researcher wishes to study the relationship between education and income separately for individuals who have college degrees and who don't. To this end, he interviews 100 individuals in each category. Those are the survey results. And so do we want to like run through all of this or skip to D or C? Okay. Well, yeah, we did B, I guess. Use the data above to find point estimates for regression coefficients, beta naught and beta 1 for non-college graduates and graduates. Okay, so he's going to ask you for all of your regression coefficients. You know, let's do non-college graduates. So, okay, first of all, man, I should stop erasing stuff that I need. Yeah, but my camera won't record them.
Yeah.
Okay, so we know that beta naught is what? How do we find beta naught?
Mean of y
Boom.
minus
Yep, how do we find beta 1?
P or rho times SY or
Okay, perfect. So we just plug those in. So we have non-college graduates first. And we have a mean of what? What's our mean? Just tell me these things.
So, wait, what are we regressing on?
Non-college graduates. Tell me the mean of y, mean of x for non-college graduates. Oh, I get what you're saying.
So I think it's education to predict income. Probably like he typically likes to do.
That would make sense. Yeah.
I can start reading them off.
Okay.
So
So y bar would be
non-college.
yeah, and y bar would be education. Yeah? Or no. Income.
Income.
Average income.
The average income, we got 67,200. This is non-college. We don't have beta 1 yet. Let's do beta 1.
Okay, fine. Let's do beta 1. What's the correlation coefficient on non-college? 0.25.
Standard deviation of income 9,400.
9,400.
And then it's going to be divided by 2. 2 is the standard deviation.
Okay. And do you have that?
But I can.
1175. Okay, plug that in here.
Yep.
1175 times average x.
Is going to be
13. And what does that equal?
51,925.
Okay. 51,925. So that's beta naught. That's beta 1 for non-college. And you guys could do the same for college. Are you okay if we skip that part? Okay. All right. Part C. Assume the error terms for non-graduates and graduates are both distributed normally, which implies that the beta hats are normally distributed with known standard deviation of 10,000. In that case, determine the standard error of theta hat. Theta hat. Oh, your estimator from before, along with the shape of its distribution. So, theta hat we just find as what? The beta 1 for G minus beta 1 and G. Okay, that's beta hat. We want the estimator or the standard error for beta hat. That's what it asked for, yeah?
Yeah.
Standard error for theta hat is the standard error for theta hat.
We know the standard deviation of the standard errors.
Yeah, maybe we should get the variance of theta hat. That's easier. variance of theta hat is going to be the variance of beta hat 1 g plus the variance of beta hat 1 and g. Are they independent? Okay. That's interesting. So they have a correlation coefficient, and yet he does not put a covariance in there. So
Here's, can we use this formula? 1 minus the variance of our error terms divided by the variance of y is equal to the correlation coefficient squared.
yeah.
Is that like what we need to use in this one, or am I thinking that wrong?
No, I mean, looking at the answer key, he just does this. He does not include covariance in here. I don't.
Should we just not worry about the covariance?
Yep. I think that's what that means. Do not worry about covariance when you're doing stuff like this.
Well, if we think,
Okay.
think of these as like samples and it truly is IID and you replace, then are they correlated or no? Because it's like the samples draw from the same population, but when you take one sample and if you completely can replace when you draw a sample again, then do we say they're correlated or are they not? It's like they're the same population, but taking one sample doesn't really
Yeah.
replace them.
I don't know. I think if they have a correlation coefficient, they're correlated, but I would ask Dr. McMurray about this one. Yeah, I don't know why he does that, but hey, I'm not going to complain. So basically, we're going to plug. This is what he does. He just does the sigma squared of the epsilons over the SSX. This is why. So like, does this? Were you taught this for standard error? Does this look at all like, even if I replace SSX with like s squared of x, does that look familiar?
S squared. That's what it says on the.
Well, he puts SXX. I'm just trying to find out if that's the same thing as SX squared, because that's what we were thinking. But
That's
I
what.
think it. I've seen it before. The SXX is like the of x
because this isn't even the formula you guys were taught. You guys were taught. You said it was. Said it was what, n minus 1 times that, which is close.
What is it actually?
Like, I mean, this is what he puts, and this is what you guys learned. So I mean, those are super close, but like,
What do you think it is?
Not with the answer keys.
I'm kind of leery of this question because of the whole SXX thing. Like, I don't trust it.
Yeah, that's what I thought it was, but I could get the answer.
Yeah, the SXX thing is not something that he's taught, and like, these are not the standard errors you guys were taught. If I was doing this question on an exam, I would just use the formula you guys know for standard errors and plug that in there.
Write down your assumptions.
Yeah, I mean, unless n minus 1 happens to be 1 in this case, but it's not. That would be crazy. Yeah. Yeah. So I think that is just, I don't know what the SXX thing is. You guys won't be tested on SXX because you never learned SXX. So yeah. So throw that question out. I think did he say, like, it's been a long time, but I feel like he said to throw one of these questions out. Oh, that was on the homework.
Yeah.
Okay. And D, using the estimator defined above, maintaining the assumption that the variances are 10,000, test at alpha equals 0.05 whether the slope coefficients differ and state the p-value. So does someone actually want to come up and do this one? I think this is reasonably doable. Great.
I don't even know where to start with this. I'm not gonna lie.
So let's start at the very beginning. How do you start a null? How do you how do you start a hypothesis test?
Oh, I see. So if we want to test if they differ, is it a two-sided test then? We just say that our HO, what are the slope coefficients, is it? Is that right?
Yep. That is good. Actually, well, I mean, you could also write it like this. Like, remember, he defined theta. Like, this might help your difference estimation just to make it more simple. But he defined theta as that.
Can we just say that theta is equal to 0, theta is not equal to 0? You mean?
Yeah, you could do that.
If we put either of them, it'd be right.
Yeah, I mean, obviously, yeah, it would be the same thing. Yeah. Okay, you got your H null, you got your HA. What's your alpha? Your alpha is
5%.
and for your distribution from the last problem, you found out
They are normal.
that this was normally distributed. Is that what he said? Yeah, and the last problem you found out that that was normally distributed, and it's a standard normal. So, okay, so that's
976.
yes. Sorry, that is.
Okay. I don't. Oh boy. I don't even know if I know where to start. I'm not gonna lie. Is this a difference of means?
Yep.
So I know that we're gonna get basically. I don't know. We're gonna get like theta on the top, and we're gonna get like some 2.
That's good.
But
Yep. So a hypothesis test looks like what? So you normally have on the top.
well, we should have this, right? We should have this one, which I'll just summarize as theta, minus the expected values for these. But I think those usually cancel out to 0, don't they, or something? At least in the problems I've done, like I feel like we always end up with just this on the top.
So going back to a hypothesis test construction, it's what you observe minus what your prediction is.
So what do we observe? I don't even know.
So you're dealing with the difference, right? So you're going to deal with your observed difference.
Which is what? Was that given in the previous, like, in the problem?
Yeah, probably. So your observed difference is 1313 minus 1175.
1313. So we're going to put 1313 minus 1175 minus, you can basically call it our HO, but it's 0.
Mm-hmm.
Divide that by, first of all, your square root, oh boy,
Variance over n.
variance. And this is going to be the variance of, is it just one of these terms? Is it supposed to be, or is it supposed to be like the variance of this and the variance of that? The variance of the first term. And
Yeah.
that was 10,000. Didn't they give us that? 10,000? No, that's a standard error.
Yeah, exactly.
What's our variance of our first?
You can figure it out.
I can.
Yep. So to find the standard error of beta 1,
Standard by that, I don't think the standard error of beta 1.
I would not write it like that.
But this is the way it makes sense to me.
Okay,
Standard error.
I just really wouldn't use epsilon in that notation. But yeah, so the standard error, do you remember the formula for standard error of beta 1? If not, I can give it to you. It's a very complicated formula.
Standard error of beta 1.
Yeah. Yeah, do you want to try? Just try shooting it off.
Oh, it's the one we memorized?
This is the one I was gonna do again.
So that's that.
Is that what he gave you? He gave you n minus 1 on the bottom, right?
Oh, yes. Yes.
Okay.
Yes, that is right.
Okay, all right. So you use that bad boy?
We do have that. And that, I think, is 10,000, right?
Yep.
Wait, it's 10,000 squared? It doesn't give us a squared.
Yeah, I think he says, no, he says the variance is 10,000. Doesn't he?
It just says maintain the assumption.
Oh, no. He says this, yeah, sigma is 10,000. So yeah, 10,000 squared. Which big square root? The
I did, so it's sample error, variance of sample error terms, variance of x. And he gave us two different ones. One of them has the population, but I mean, I think this question only gives us the sample, so.
Yep. So you're going to use the sample.
And then we need the variance of x, but doesn't it give us that in the table clear above? This is going to be education. So it's 2 and 1.2. Oh boy. So 4. So that's one of the terms, right?
Mm-hmm.
10,000 squared. The other one. Squared.
1.44.
Was that written correctly?
10,000 squared over 9. Yep, looks right.
Is that what it equals?
Oh, you did the whole thing?
Or yeah, yes, it's on the answer key. C2.
Oh.
0.14. 0.14? 0.14. In that case, then we look, we have 99 degrees of freedom, right? For a t-test. Which we can just round to 100 degrees of freedom. And it's a two-sided 5%. So 1.984. 1.984. We're going to multiply that by 0.14.
What's the 1.984?
So I took an alpha of 5%.
Uh-huh.
So I basically did a two-sided 5% alpha of 100 degrees of freedom. Looked on the test and found 1.9.
Okay.
Does that sound good?
And why are you multiplying it by 0.14?
That is a great question.
Oh.
I didn't think before I did it.
Okay. So you got 1.94, and what is 1.94? What?
It's a critical value, right?
Okay. So if that's your critical value, you compare it against.
Plus or minus.
That comes straight from your alpha.
Oh yeah, I don't want to multiply this by 1. I want to take.
So what do you compare critical
I
value
need
to?
a test statistic.
Okay. Yep.
But I'm gonna need to multiply this by some number. I'm gonna have to add it to probably.
Yeah. I mean, is that not your test statistic?
0.14, is it?
It is, yeah.
Oh,
Yeah.
it is?
Greater than
Oh, you just
0.05.
compare it to that one? Yeah. So that. Well, we're not done, but we've done the math. Now.
Yeah.
So we
So it's
we
less
accept the null hypothesis.
Um,
We
so
fail to reject.
We fail to reject the null hypothesis.
Yeah.
I hate that wordage. We fail to reject the. It's just like just say we accept the null.
Yeah,
Don't say we fail to reject the null. Just say we accept the HA.
Yeah. You don't. Yeah.
And then the second part, it wants us to state the p-value associated.
So
How would we do that?
Yeah. So it's weird in this question. 0.14 is your test statistic.
how do you do that though when this graph under 100 degrees of freedom?
It's
Like-
normal. It should be normal.
It should be normal at this point now.
Yeah. So your test statistic,
You don't plug it into degrees of freedom.
you get 0.14. So
That can be kind of.
So am I looking at this right?
No, wait. 0.14. You're looking like somewhere around right here. 0.14. No, wait. Oh no, you want to do 1.14. I was finding 0.14 inside the table. You want 0.14 to be. You want 0.14 to be your outside. It's the number.
Yeah, that's what I'm confused about. Is that's your test statistic? So you're kind of like.
That's a pretty crazy test design. Isn't that a massive p-value?
Yeah, he got point. Okay. So 0.14, and then you would divide that. No, you wouldn't divide it. Okay, so 0.14 on your z table gives you 0.5557.
We have a 55% p-value.
Wait, how'd you get 0.555?
So yeah, I know it's weird because we usually don't see test stats of 0.14. But like,
Oh, okay.
but this is what happened. We got like here, we got 0.14. And that is our test stat. So our p-value is that.
Does it change the fact that this is a double-sided? Do we have to alter our p-value at all?
Yeah, I think you do. Yeah, you multiply that by
By 2?
2. Yep.
So it's 110% p-value?
Well, no, sorry. Your p-value is less than 50%. Okay, so you would do 1 minus what you found.
Oh, so it's 1 minus this.
Yeah,
What you're
yeah.
saying?
This is less than 50%.
Oh, I see. So it's a 90% p-value.
Yeah, your p-value is pretty much 90%.
Okay, when I was doing my data project, my test statistics were like 54. My p-values were like
Yeah,
basically
so
0.
that's your p-value right there.
Wow. That was a hard problem, I'm not gonna lie. So that was a hard one.
That's okay, but like you guys get like the main things that you're supposed to get, right? If you get confidence intervals, if you get hypothesis tests, and if you just understand standard errors, like that's a like huge bulk of the test right there. And then just like when you get to a problem, even if you don't like know how to do the problem, if you don't know how to get to the answer, like you know about these concepts, so just like write down what you know.
Who's grading it? Are you going to grade them? Or is Professor McMurray going to have to grade all of them?
He will not grade, the TAs will grade. So
Pressing on your partial credit.
yes, I will not be more harsh than I was on the last one.
No, it was something weird. It was like a typo on the works on it.
Yeah.
I remember trying to do it.
It was like question 10.